Hi to this quick guide on how to run Urban Tethys Chloris, in short UT&C. I will first show you how you can set up the model, specify your geometry and what sort of inputs are needed. I will then do some code demonstration. I will show you some examples of the output. And last, I will discuss some problems which you could run into and how to troubleshoot them. First of all, what sort of inputs are required to run the model? You will need meteorological input time series at forcing height, and you will also need to specify a number of model parameters which characterize the urban area which you would like to simulate. I also would like to highlight that there is an extensive technical reference manual provided as a supplement to the main model description article published in GMD. Hence, if you would like to know more about the physics which is applied in the model, as well as the parameters, have a look there. I would like now to go a bit more into detail into what sort of meteorological input is required and the model parameters. You will need to have date and time in MATLAB datetime format, incoming long-wave radiation, incoming short-wave radiation partitioned into its direct and diffuse parts, temperature, wind speed, atmospheric pressure, precipitation, and relative humidity. There is another short tutorial which will show you how you can compute incoming long-wave radiation in case you do not have this measured, and how you can partition incoming short-wave radiation into its direct and diffuse parts. Please also be careful with the units so you get a realistic output. You will also need to specify the location you would like to simulate in terms of latitude and longitude, the canyon orientation, the difference to Greenwich Meridian time, and you will also need to specify at which height your meteorological measurements are measured. Note that the atmospheric forcing or reference height always needs to be above the canyon. The canyon orientation specifies in which direction your infinite urban canyon is located to. As you know, a realistic urban environment has a lot of different street directions. However, how I usually solve this is that I'd specify the major street directions, for example, shown in this picture here, and I'm simulating both of them or all of them, and I'm averaging the output afterwards. Note that the canyon orientation is measured as an angle from north. There are a number of parameters specifying the urban geometry, such as building height, canyon width, roof width, impervious bare and vegetated ground fractions, vegetated and impervious roof fractions, tree height, which is from the ground to the middle of the crown, radius of the tree, and the distance of the tree from the wall. Note that the impervious and vegetated roof fractions, as well as impervious bare and vegetated ground fractions, each need to sum up to 1. Also, the total tree height, which is the height of the tree plus 1 radius, cannot be higher than the average building height. Besides urban geometry, there is a large set of model parameters. You will need to specify radiation and heat transfer parameters, vegetation parameters, soil parameters, anthropogenic heat and water settings, as well as mean radiant temperature settings. A description of the model parameters can be found in the technical reference manual, which was provided as a supplement to the main model development article in GMD. You can have a look at supplement table 1 to 4, which show the parameters used in the model validation in Singapore, Melbourne, and Phoenix. This is the technical reference manual, which is provided as a supplement to the model description article published in GMD. In section 9, model input parameters, you have table 1 to 4. In each table, you have a list of parameters, their description, and the values which were used in the model validation in Singapore, Melbourne, and Phoenix. Table 1 contains urban geometry, radiation, and conductive heat flux parameters. Table 2 contains vegetation parameters. Table 3 contains soil interception and runoff parameters. And Table 4 contains location and measurement parameters, as well as the anthropogenic heat flux used in the model validation. Additionally, a range of vegetation parameters is provided in Table 1 in the article Vegetation Cover and Plant Trait Effects on Outdoor Thermal Comfort in a Tropical City, which was published in Building and Environment. In this article, in Table 1, you have the list of vegetation parameters and a possible range, which could give you an idea if you would like to play around or vary the vegetation parameters. Another thing which I would like to highlight is that you will need to specify the height and the position within the urban canyon at which you would like to calculate mean radiant temperature, which is then afterwards used for the calculation of outdoor thermal comfort. Okay, so now that we talked about all the model parameters and inputs required, let's have a look at the code structure. When you open the UT&C code in MATLAB, you will see that there are a large number of folders as well as functions. The folders starting with a plus contain a lot of different functions for the calculation of the different physical processes. The main script to start the computation is called computation plus the name you give it, and the outputs of the simulations are saved in the calculation plus the name you give it .mat files. There are a number of scripts and files which you will need to know, and they're located in the data functions subfolder. There are two files specifying model parameters and forcing data. The first file is named data UEHM site plus the name you give it, while the second one is called UEHM forcing data plus the name you give it. In the subfolder data functions, you will also need to save your meteorological input forcing data and the time-varying leaf area index data file if you would like to provide that. The internally calculated view factors are also saved in the data function subfolder. Furthermore, I would like to emphasize that you should not change the folder structure or rename the folders and the scripts, as this might lead to a crash of the model. When you download the code and you open it in MATLAB, you will have an example included which you can run straight away. In my case, this is the simulation of 3 days in Zurich. To run this simulation, I can open the Computation Zurich file in a main folder, and actually I can just press run. You will know that the computation is running when you see these numbers here advancing. You will know that the computation is done when you get this output written here, which shows the total time which elapsed for the simulation. You will also get a number of output plots, which I will talk about later. I would like to quickly highlight the numbers which were printed in the command window. These numbers here show the simulation step at which your simulation is at. This can be useful when you're simulating long time series, and while the code is running, you would like to have a look how far your simulation has progressed. So now that we have run this very simple example, let's have a look on how to modify the code so you can run your location. First of all, let's open the data functions folder, and let's have a look at the computation Zurich file. The computation script is the main script to start the simulation. In this script, you will first load your meteorological forcing time series. You have pre-prepared this, and you will need to put the name of your data file here, which you will need to save in the data functions folder here. Second, you can provide a time-varying leaf area index input. If you do, you put a 1 here, and you will need to save your leaf area index time series in the data functions folder. If you do not provide a time-varying leaf area index, just put 0 here. The parameter n specifies the number of time steps of your simulation. I've calculated this here internally. However, if you would like to specify this manually, you can also do this. For example, my simulation here had 72 time steps. Hence, I could put 72 here and comment the rest. It is likely that you would like to simulate more than one location. And for this, you most likely also would like to have outputs with different names or to specify parameter files with different names. Hence, the parameter files and the output can be customized with the name underscore site, the name underscore site FD, and the name output parameters. For example, here I all called them the same, set age, which stands for Zurich. And this set age here means that my data underscore UEHM underscore site file needs to have the ending set age here. The same goes for the UEHM forcing data underscore file, which is specified here, the set age as well. And then for my name output, I also specify set age, which corresponds here. As you can see, there is also a second calculation saved here with the name calculation set age 2010. This is actually a simulation of a 1-year time period at the same location. To change this name automatically for the simulation, I just added here the underscore 2010, which then, after I run the model, saves me the simulation automatically as calculation set age underscore 2010. I just would like to emphasize that while I changed name here, the output will automatically be saved with a different name, that in these two parameters, you will actually need to make sure that your two data files, this one and this one, have the appropriate naming to be found by the main script. So what do you specify here? Whenever you start a simulation with a new geometry, you will need to recalculate the view factors. This can be done in setting the option ray parameter to 0 and starting the simulation. View factor calculation will take a short while as the view factors are calculated with a Monte Carlo ray tracing algorithm. During the view factor calculation, you will get an output graph looking like this. This graph shows the urban geometry for which the view factors are calculated. Here you have the two trees, and here is the point at which the view factors for the mean radiant temperature are calculated. This graph also gives you a short idea on how your geometry looks within the model. After the view factor calculation, the view factors will be saved in the file viewFactor underscore the sitename.mat in the data functions folder. This gives you the option to use the pre-calculated view factors, and for this you set here a 1. This is helpful if you're not changing the geometry for a subsequent run and saves you time during that simulation. Now there's one more thing to do in the computation file. All in the beginning, we're loading the meteorological time series, which is saved in the metadata file. What we now also need to do is when we scroll down, we need to assign the appropriate meteorological variable, which is saved in this file here, within the struct metadata row. For each variable, for example, here we have incoming long wave radiation, we need to write here the name of the variable incoming long wave radiation as it is saved here. One thing which I would like to emphasize again, please be careful with the units which are specified here again. If you put the wrong units, the code could crash or you get an unsound output. One thing which could happen, and I quickly would like to show, is that actually one of your input variables or meteorological input variables is in the wrong unit. In my case, that was relative humidity, which was in % in my metadata file. However, the model requires a fraction. This can easily be solved when you're assigning the meteo variable in the data struct. For example, here in relative humidity, I just divide my relative humidity by 100, which solves my problem. One thing which I would like to emphasize here is that when you're dividing, or when you would like to divide by element in MATLAB or multiply by element in MATLAB, you always need to put a point in front of the division or multiplication. So now you're all set in the computation file, and from here downwards, you will not need to change anything for the code to run smoothly. Let's look at the two files in which you're specifying the parameters of the site. Let's first have a look at the data underscore UEHM underscore site underscore ZH, or your name file. In this file, you will specify the urban geometry, as well as parameters related to radiation and conductive heat fluxes, soil, vegetation, and so on. So in this file, you're really specifying your urban setup. I will now quickly scroll through the script and show which parameters you can set. Very first, you can specify the geometry of your urban area. You can do this with the average canyon height, the canyon width, the roof width, the radius of the tree, the height of the tree, and the distance of the tree. These parameters here are required in meter. After each parameter, you will always find a small description of the parameter as well as the units which it requires. One thing which you might be wondering is why I'm including the radius tree here in the assignment of the average tree height and the distance of the tree from the wall. Well, the total tree height is actually the radius of the tree plus this height of the tree. Hence, because I determined my total tree height beforehand as 5, I'm subtracting the radius here. Similarly, the distance of the tree from the wall includes a small distance of the tree crown from the wall plus the radius of the tree. Hence, I'm doing this here. However, you do not necessarily need to include the radius tree in these two places if you're determining beforehand that your geometry is how you want it to be. The model includes two parameterization of aerodynamic roughness. One that does not account for building height variability and one which accounts for building height variability. If you want to account for building height variability, you need to set numbers for the maximum building height as well as the building height standard deviation in these two parameters. However, if you would like to use the original formulation, which I would recommend you to do, use the not a number here, which is already pre-assigned. The following parameter trees is an easy switch to include or exclude trees in the simulation. If you want to include trees, put a 1 here. If you want to exclude trees, put a 0. The parameter f3 is currently not implemented in a model, hence do not change it and just leave it as 1. Scrolling down, we see that there are a number of parameters which are calculated internally. Hence, you do not need to change anything here and just leave it as it is. The next parameters which you would like to assign are related to the surface fractions. You can assign here the vegetated roof fraction as well as the impervious roof fraction and the vegetated bare and impervious ground fraction. Make sure that the fractions on the roof as well as on the ground add up to 1. Another parameter which you will set is the percent runoff on the roof and the percent runoff on the ground. These parameters specify the percent of excess water which leaves the system right away. This means this is the water which is in excess of the maximum ponding capacity on the roof and the ground. On the roof, I specify this as 1, that meaning all the excess water leaves the system straight away. And on the ground, I specify that this as 0.9, meaning that 10% of the excess water will be brought forward to the next time step and redistributed on the ground surface. These two values assigned here are obviously just examples. You can change this in your simulation if you would like. The next set of parameters which you will need to assign are related to the vegetation properties. We assign vegetation parameters separately for roof, ground, and trees. The very first parameter is the constant leaf area index. If you're using a constant leaf area index, assign your value here. The second line, also referring to the leaf area index, does not need to be modified. It is only used to determine if you're using a constant or a time-varying leaf area index. I will not go through each of the vegetation parameters separately, but I refer you to the technical reference manual as well as the vegetation parameter sensitivity analysis article which I showed you before. If you cannot find a vegetation parameter in either of the tables in these articles, for example, these 3 parameters are not included, do not change them. The same set of parameters is also assigned for the ground vegetation and the trees. This does not mean the same values, just the same set of parameters. Next, you will assign all the optical properties. This means the albedo and the emissivity for the roof, for the ground, for the walls, and for the trees. Similarly, you will assign thermal properties such as conductivity and heat capacity for each urban facet. Next, you will need to specify the thickness of your solid layers, such as, for example, your roof or your wall. You will also need to discretize your soil layers, for example, done here for the roof, it's in millimeters, and for the ground. In this location in the code, you also have the ability to specify that you would like to fix soil moisture to field capacity in certain layers. If you would like to do so, you can set the one here, and you need to specify your start and your end layer. Note that the first layer is the layer all at the top, and the largest number is the layer all at the bottom. Next, you would like to specify, or you need to specify what sort of soil you would like to model. For example, in this case, we assign a sandy loam, which has a fraction of clay, sand, and organic material. If you're unsure about the soil, just use this sandy loam. This is for the roof and also for the ground. In this section, you can also specify your maximum interception capacity on the ground and the vegetation, as well as a number of soil hydraulic parameters. The last set of parameters which you will need to specify in this file are related to the calculation of mean radiant temperature. You will need to specify the position in the x-axis and in the z-axis within the urban canyon at which you would like to calculate mean radiant temperature. You can also specify a height at which you would like to calculate wind speed to calculate outdoor thermal comfort. So now that we're all done setting up the urban area in the data file, I will now show you what you will need to set up in the UEHM forcing data file. The UEHM forcing data file contains a number of parameters which are related to the urban location as well as the meteorological inputs. There are only a number or very few parameters which you actually need to assign, and I will show you these now. Here you will need to specify the latitude and longitude of your location, the canyon orientation, and the difference with Greenwich Meridian Time. You will also need to specify the atmospheric reference height, which is the height at which your meteorological data was measured. This height needs to be above the urban canyon. In this file, you will also need to specify a number of anthropogenic factors, such as the minimum, maximum interior building temperature. Generally, the interior building temperature is equal to the temperature at atmospheric reference height. However, if this temperature is below the minimum or maximum value, the interior building temperature is fixed at these values. This corresponds to building heating and air conditioning. Furthermore, you can also specify an anthropogenic heat input into the canyon air with this QF canyon. Note that anthropogenic heat at the roof level with this QF roof is currently not included in the model. Hence, if you're assigning something here, it's not going to be used. Another input which you can specify in this file is an anthropogenic water input. This specifies the irrigation at the ground surface, such as, for example, for vegetated ground fraction in the canyon, bare ground fraction in the canyon, and for the vegetated roof fraction. Note that the values you're assigning here are in millimeters per time step. If your time step is 1 hour, these are millimeters per hour. However, if your time step is half an hour, this will be millimeters per half an hour. Hence, be careful what you're assigning here. So now you're done with the definition of your urban area. And if you're not providing a time-varying leaf area index, you can start your simulation now. To start your simulation, just open the computation file. Make sure that the names correspond to your file's in here, and that you have the name which you would like for your output, and you can start the simulation. At the end of the simulation, all the calculated variables and simulation outputs, which are listed all at the end of the computation file here, are saved in the calculation.mat file. At the end of the simulation, there will also be a couple of output plots, which give you an initial idea about the simulation results. I will go now one by one through these plots. The output plots show you generally the diurnal and the seasonal cycle of different output variables, such as, for example, the shortwave radiation, longwave radiation, and the urban energy fluxes. You will also get the same graphs for albedo and Bowen ratio, the water fluxes, surface and air temperature, as well as relative humidity, outdoor thermal comfort, and mean radiant temperature. The last graphs shows you the time series, the diurnal and the seasonal cycle of the energy and the water budget closure. At some time instances, the numerical solver is not able to converge and you will get a non-closure of the energy balance. On average, however, these values should be very small and your simulation should be okay. Once your simulation is done and these output graphs look fairly fine, you're likely to do your own analysis with the saved simulation outputs. Hence, let's have a look at them. After your simulation is done and you cleared the workspace, you can reload the simulation output when you're loading the calculation.mat file. There are a large number of variables calculated and saved as a result of the simulation, and they're all listed now in the workspace here. To get an idea what is stored in each of these variables, you can actually scroll through the computation file. At the variable initialization, you will get the name of the variable, the name of the subvariables it contains, and a short description of them. Hence, if we're interested in temperature, we can locate the temperature vector here. And when we open it, we see that it contains a lot of subvariables as well. For example, from the atmospheric temperature to the tree temperature, the impervious roof temperature, and so on. If we open now one of these vectors, for example, the tree temperature, we see that the tree temperature vector contains the simulated time series of tree temperature. With this method, you can find the output which is of most interest to you. For example, the surface temperature, which is stored in TempVec, outdoor thermal comfort, which is stored in UTCI. If you want the air temperature or the relative humidity at 2 meter height, this is stored in results 2 meter. Or you could be interested in mean radiant temperature. The water fluxes averaged for the canyon, the roof, and the total urban area can be found in these respective variables. Similarly, the energy fluxes for canyon, roof, and urban in total are stored in these 3 variables. So now you should have all the information to easily run the model, set up your own urban geometry, and to analyze the outputs. There is one more thing which I would like to mention before we move on to the troubleshooting section of this tutorial. The initial simulation which I showed you was a 3-day simulation for the climate of Zurich. However, there is also a longer time series of meteorological data included in the code which you downloaded. When you open the data functions folder, there is the forcing data _ZH 2010.mat file, which contains a 1-year time series of meteorological input forcing. If you would like to perform a 1-year simulation, all that you need to change is to load this data instead. Also note, if you're not changing the name of the output, you will override your initial calculation. Hence, what I do here, I change my output name to 2010, which will save my simulation output later on in the calculation ZH _2010. This is the output which I saved from a previous calculation. With this, we can just start and simulate the 1-year period. Note that this will take quite a while, and we will not wait for this now in this tutorial. One thing which I would like to mention is that these output graphs, which I showed you previously, are actually the output graphs of the 1-year simulation. In the simulation where you're only simulating 3 days, you will not get a seasonal output as there is no data for this. So now that we're almost at the end of this tutorial, I would like to mention a couple of common mistakes which can lead to an error message and to a crash of the code. One of the problems you could experience is that you get an error message which is related to the tree or the canyon geometry. To fix this, check that your specified tree and canyon geometry actually makes sense. For example, the trees cannot be higher than the average canyon height, which is shown here. The trees cannot overlap with the wall or the ground, which is shown here. Their atmospheric reference height, which is shown here, needs to be higher than the average canyon height. The roof and the ground fractions, these and these, both need to add up to 1. Or it could also be that you forgot to recalculate the view factors after you changed the canyon and tree geometry. In this case, you will get an error looking like this. Last, we also experienced that UT&C crashes in some newer MATLAB versions or releases. To fix this, we found that actually just reinstalling or updating MATLAB again or changing to a different MATLAB version solves the problem quite easily. With this, we're at the end of this quick guide on how to run Urban Tethys Chloris. I've also listed here a couple of references which are related to the model.